In this video, I'd like to talk a bit about complex number multiplication and some of its quite remarkable properties. And to kick off this video, before getting into the mathematical meat and potatoes, I'd like to show you a quick visualization. Now, what I've done here is I've taken the two-dimensional grid with x and y axes, and what I've done is I've randomly generated some points, and I'd like you to think of each one of these points as representing some complex number. Now, what I'm going to do is I'm going to take each one of these dots, each one of these complex numbers, and multiply each one of the dots by another complex number. And we're going to observe the effect of multiplying each one of these dots by another complex number. So what I'd like you to do is pick any one of these points, let's say that one, or any point you wish, and keep your eye on it. And now have a look at what the effect of multiplication by a complex number does. And hopefully you can see that each one of these points has been rotated just slightly. And if I apply this operation a few more times, doing that same operation, and one more time, we can see that each of these points is being swept out along these circular trajectories. For example, if we started that point there, it's been transformed to that point first, then that point, and then that point. And the big question is, mathematically, why is this the case, that complex number multiplication generates these circular orbits? In addition to the rotational properties of the complex numbers, there's one additional very interesting property that I'd like to show you in this second visualization. Again, what I've done here is generate a bunch of random complex numbers plotted on the two-dimensional grid. And this time I'm going to multiply by a slightly different complex number than what I did before. And again, what I encourage you to do is pick any one of these complex numbers and follow it with your eye as I successfully multiply it by this other complex number. And let's see what happens. That's one multiplication, and again, and again, and a last time. And hopefully what you're seeing here are these spiral-shaped trajectories of each one of these dots. And what I claim here is what we're seeing here is a combination of the rotational property that we saw in the previous visualization and one additional property of complex number multiplication, which is its scaling ability. What I'd like to do at this point is explain to you why it is that we're seeing these rotational properties of complex number multiplication. And to do that, I'd like to give a very quick review of complex numbers, just to make sure we're all on the same page. Now, of course, the defining property of the complex numbers is that we have this object in the complex numbers, I, that has the property such that I squared is equal to minus 1. And of course, this is significant because no number in the real numbers will have the property that it squares to minus 1. Of course, every real number either squares to 0 or something greater than 0. There's no number that squares to minus 1. And what we're going to do here is we're going to take two real numbers, let's call them A and B. This second number, B, is going to multiply I. It's going to scale I. It's going to tell me how many copies of I you have. And then we're going to join these two things together. And we're going to generate these new objects, which are going to be written in the form A plus BI. And this is going to be the set of complex numbers. Now, this is one way to think of complex numbers as numbers of the form A plus BI. There's another more formal way of thinking of them, which is also much more suggestive for plotting them, which is just an ordered pair of two real numbers, A and B, written as coordinates. Now, these two ways are equivalent, but this second notation is a bit more suggestive in that it suggests we can plot these objects A, B on a two-dimensional coordinate grid. What I'm going to do here is draw the horizontal axis to denote the real component, that is this first component A, and this vertical axis to represent the imaginary component, which is going to be B. And of course, this A is called the real part of the imaginary number, and B is called the A is the real part and B is the imaginary part of a real number. So if I have this two-dimensional coordinate grid, some point AB is going to be plotted by going A units on the real axis and by going B units on the imaginary axis. And hopefully this is very familiar to most people watching this. And now, probably the most interesting part of complex number arithmetic is the sort of multiplication that this I squared equals minus 1 generates. Now, suppose we have some complex number, a plus bi, and I want to multiply it by another complex number, let's say c plus di. And again, a, b, c, and d are just some real numbers. Now let's go right ahead and distribute everything. So I'm going to distribute the a to c plus di, and what I'm going to get is ac plus ad times I. Now let me distribute that bi to these two terms. So I'm going to get next, I'm going to get b times c times I, or b ci. And then finally, I have b times d times I squared. So bd I squared. And now let me simplify. I have AC, and then there's not much I can do here. ADI plus BCI. Now remember I squared, and this is the algebra that we're going to generate. This I squared is going to be minus 1. So this turns into minus BD. And notice here I have two terms, AC and minus BD, which are going to be the new real parts. So I'm going to group those together. AC minus BD. And then I have two terms, ADI plus BCI, which are going to be the new imaginary parts. So I'm going to group those together as well. So I have AD plus BCI. And this is how we're going to define complex number multiplication. That is to say, if I have two ordered pairs, let's say I have the ordered pair AB, and I have a second order pair, CD, we're going to define multiplication. This is what the dot is going to mean. Complex number multiplication is going to generate the following order pair. AC minus BD in the first entry as that new real part, and then the new imaginary part is going to be AD plus BC. So there you go. There's the definition of complex number multiplication. And this definition is very interesting too, because just by following this rule that we've defined, you can see that the order pair 1, 0 behaves like 1, in that if I have 1, 0 and I multiply by any other complex number, that will not change the complex number. It acts like a 1, seeing as how multiplying by 1 doesn't change anything. And in addition, if you take this other order pair, 0, 1, and if you multiply by itself, that is to say you square it, you get minus 1, 0. And since 1, 0 acts like 1, negative 1, 0, quite expectedly, is going to behave like minus 1. So here you have some number, which is going to be I, being multiplied by itself, or squared, and that's going to generate minus 1. So we indeed have some object in this field, the set of complex numbers, namely 0, 1, which is going to behave like an I, a number that squares to minus 1. Let me go back to that diagram real quick. Now, let's suppose I have some complex number here called AB plotted out on this two-dimensional grid. Now notice I can form a triangle from this point. I'm going to drop a vertical line like that, and the length of that is going to be B, and the length of this leg here is going to be A. And I can complete a right triangle, just like so. And by the Pythagorean theorem, the length of this hypotenuse here is going to be the square root of A squared plus B squared. That'll be the length of that hypotenuse there. Now, very naturally, we can define a sort of distance with this complex number AB. That is, we can define the distance from that point to the origin. And it's going to be given by precisely this quantity, the square root of a squared plus b squared. So let me write out precisely that. So I have some complex number AB, and I'm going to define the magnitude, which is going to be denoted by these absolute value bars. The magnitude of AB is going to be the square root of a squared plus b squared. And again, this is a measurement of how far this complex number is away from the origin. This quantity goes by a number of different names. I call it the magnitude. I think that's the most intuitive. It's also called the modulus, I think. Some people just refer to it as the absolute value. And one other thing I'd like to point out here, hopefully this is quite obvious, that if I have the magnitude of some number AB squared, its squared magnitude is just going to be the sum of squares of the components. Just a squared plus b squared. And hopefully all of this so far is a review. But what I'd like to really point out in this video is something many people may not know, is that when I take complex number multiplication and relate it to this distance or this magnitude function, there's a key property that is preserved. And that's what's going to allow for this rotational property of the complex numbers. To show you that, let's suppose I have some complex number, x, and I multiply it by another complex number, y. And suppose I'm interested in that magnitude. Now, I claim that the magnitude of x times y, where times just means complex number multiplication, is equal to the magnitude of x times the magnitude of y. This is seemingly a very natural property. And to demonstrate this, I'm going to actually show something different, which is that the squared magnitude of x times y is equal to the product of squared magnitudes of x and y taken independently. And I square it just to get rid of the square root, and it's going to make it much more clear to show it in this way. Here's the claim written out once again. Suppose x and y are two complex numbers. Then I claim it's true that the squared magnitude of x times y is equal to the squared magnitude of x times the squared magnitude of y. And again, the squared magnitude of some complex number a plus bi is going to be a squared plus b squared. Now let me do precisely this. Let me suppose that x is equal to some complex number a plus bi, and that y is some other complex number, c plus di. And now, what is x times y? That's precisely what we've been talking about before. So that's going to be this other complex number, ac minus bd plus ad plus bc times I, and I have the squared magnitude of that. And I'm going to work with the left-hand side for now. And this is just copying out that definition, as you can hopefully see. So what is the squared magnitude of this quantity here? That's just going to be the square of this first real part, which is AC, minus BD all squared, plus the square of the imaginary part, which is going to be AD, plus BC all squared. And now I simply square this quantity here, which upon squaring is going to be a squared, c squared, minus 2 times AC times BD. I'm going to write that in the order 2 ABCD. And then that last term is going to be plus b squared d squared. And now I'm going to square out this second term here. I have plus a squared d squared plus 2 times, again, we see a, b, c, d. So 2 times a, b, c, d. And then finally, I have plus b squared times c squared. And now we have a look. We see that we get this nice cancellation here. And I have 4 terms remaining, and I'm going to write them in a slightly different order. I'm going to first write a squared times c squared. Then secondly, I'm going to write this term here, plus b squared c squared. And then let me write this term next, a squared d squared. And then finally, I have b squared d squared. And now what I'm going to do is, out of these first 2 terms, I'm going to factor out a c squared. So I factor out that c squared, and I have a squared remaining in the first term, and then plus b squared left. And now out of these second 2 terms here, I'm going to factor out a d squared. And again, I have a squared left plus b squared. And now I notice that I have 2 terms here, and both terms have a factor of a squared plus b squared. So I'm just going to factor that out of both terms. A squared plus b squared times c squared plus d squared. And now notice that a squared plus b squared, well, what is this? If I go back up to the definition of x was a plus bi. Now this is just the squared magnitude of x. And here we have c squared plus d squared. Going back up to the definition of y, I see that that's the squared magnitude of y, c squared plus d squared. And now I've shown that this quantity here, the squared magnitude of x times y, is equal to the product of squared magnitudes of x and y taken individually. Let me write that statement that we've just proven in a slightly different way. So we have that the magnitude of AB is equal to the magnitude of A times the magnitude of B. And hopefully you can see that the statement about the squared magnitudes implies this statement about the non-squared magnitudes. And I'm just changing up the letters to A and B instead of X and Y. Now, what I'm going to do here is I'd like to pick some complex number B such that the magnitude of B is equal to 1. And what does that mean graphically? Now, what it means is that we have some unit circle, and I'm going to pick some point on the unit circle. Let's say right there. That could be B, because unit circle is the set of all points such that the magnitude is 1. So B could be any point on the unit circle there. Now, if B is selected to be of magnitude 1, what does that imply about the magnitude of AB? Well, we see that the magnitude of AB is equal to the magnitude of A times the magnitude of B, but B was selected to be 1, so it's going to be 1. So what that means is that when I take A and multiply it by B, that magnitude is precisely the magnitude of A. Now, let me illustrate that a bit more graphically. Let's say I pick some point out here. Let me call that A. What is the magnitude of A? It's just the length of that point drawn to the origin. So that length of the line right there is going to be the magnitude of A. Now, what is the set of all points that has magnitude of A? Well, that's just going to be the circle that's being swept out by that radius, magnitude of A. So any point on that blue circle is going to have the same magnitude as A. Now, since we just found that the magnitude of AB is equal to A, that means that the value of AB, that point must be located somewhere on this blue circle. Wherever it is, it has to be on this blue circle here, because its magnitude is equal to that of A. So AB could be there, for example. And of course, just to draw this in, the length of this green line connected from AB to the origin is going to be the magnitude of AB, and the magnitude of AB, that green line, is going to be equal to the magnitude of A, which is the length of that blue line there. Now, what does all that mean? That means that multiplication by some complex number that I happen to have called B, which lies upon the unit circle, will take some other point, which I called A, and it will rotate it. And I use the word rotation because this point, as it gets sent from here to here, stays along the same circle of the same radius as the magnitude of A. It follows a circular trajectory being rotated along the origin. So that's the very special property that I wanted to point out when multiplying by a complex number of unit length, which is all made possible by this key property here, that the magnitude of AB is equal to the magnitude of A times the magnitude of B. So that seemingly uninteresting algebraic property turns out to explain why we get rotations in the complex numbers. And let me put this to you in a different way. And this is going to be very helpful for understanding the visualizations that I showed you in the beginning part of the video. Let's go back to that unit circle. And remember, we were picking these points kind of at random. But it turns out that where you pick B to be on this unit circle can control how much rotation you have. For example, if I pick B to be right there, if B is just equal to 1, A times 1 is just going to be A. So that means that by multiplying by this number, which is just 1, we get no rotation at all. That is, if I have some arbitrary point, let's say A out here, that A times B doesn't do anything. It just holds that point there steady at A. Now suppose I pick B to be not right there, but just slightly above. Let's say that's B. Let's say it's rotated by just a few degrees with respect to that first B. Now, when I multiply by this new value of B, since this first value of B did nothing, this new value is going to do almost nothing. That is to say, it's going to rotate A by just a very small amount. And it turns out that the amount of angle that it will rotate A by is equal to this angle right here. So A is going to be sent to that position right there, approximately. That is, say, I should say AB is going to be this new point here. Or as I put it, A is going to be sent to AB. And the second thing I'd like to point out that's going to be helpful for the visualizations is that instead of looking at the unit circle, let's look at some circle that has radius 2 instead of 1. So 1 is going to be right there. And now let me pick that B complex number to be on the circle of radius 2. And once again, I might have some arbitrary value of A, which could be located, let's say, out here. The magnitude of A is going to be the length of that line. And let me just draw in that circle there, or attempt to draw it in. And now I ask the pertinent question, where is A times B going to be located? So I know that the magnitude of AB is equal to the magnitude of A times the magnitude of B. I selected B such that it has a magnitude of 2. So that means I have that that's equal to the magnitude of A times 2. So the magnitude of AB is going to be twice the magnitude of A. So what that means is that if I take this length here and draw in a circle of twice the radius, let me attempt to draw in some of that there. this larger circle here, that AB is going to be located out here on this bigger circle. It could be located right there, for example. And the magnitude of AB would be the length of that white line there. So we can see that the effect of multiplying by a complex number, which doesn't have unit length, but instead has a length of, let's say, 2, has two effects. It has a rotational effect, that is, it takes this point A from that smaller blue circle onto a larger white circle, so it has that rotational effect, but it also has a scaling effect. That is, it moved A from a point which is closer to the origin to a point which is now farther from the origin. So I claim that this effect is twofold, that we have a rotational and a stretching factor, or scaling factor. At this point, I think we're ready to go back to those visualizations a second time, and let me show you what you're going to see. Now, in that first visualization, where I had those circular trajectories, I didn't reveal to you what complex number I was multiplying by, but the complex number that I multiplied by in the first case was I let that B number be of unit length, but the exact number that I chose was the cosine of 3 degrees plus the sine of 3 degrees times I. So this is the complex number that each one of those little dots is being multiplied by. And hopefully you can see that the magnitude of B is going to be 1. So this number comes right off the unit circle. And hopefully you can also see that B is approximately equal to 1. So it's pretty close to 1, which means that multiplication by B does almost nothing. That is to say, the amount of rotation that it exerts on any given point, let's say A is located right there, the amount of rotation that exerts on any one of these numbers by sending it to AB is quite small. And this is a function of choosing 3 degrees as opposed to, let's say, 90 degrees, which is going to rotate by quite a bit. So that's what's going on in that first visualization. And in the second one, with the spiral trajectories, what I did there was I selected that complex number B such that it was not on the unit circle, but it's on the circle of radius 1.025. And the complex number that I chose had the same angle. So the precise complex number is 1.025 times cosine of 3 degrees plus 1.025 times the sine of 3 degrees. So here we saw that by choosing a number on the unit circle, but it's located very close to 1, exerts a rotational effect only. Now here I've done the same thing. I've chosen essentially this same complex number, but it's being multiplied by some number which is greater than 1. So that means it's going to have a stretching effect plus a rotational effect. Let me show you that circular motion again, now that we're better prepared to understand what's going on here. So again, let me remind you, each one of these dots represents some complex number, and I've let the x-axis run from -1 to 1, and the y-axis run from -1 to 1 as well. So I have just a bunch of random complex numbers. I think I have 1,000 in this picture. And what I'm going to do is multiply by that other complex number, cosine 3 degrees plus sine 3 degrees times I. And we observe what happens. That's one multiplication. So this would be, as I call it, AB. I multiply by B again, so this would be ABB, or AB squared. This would be ab cubed, and ab to the fourth power. And hopefully you can see quite clearly that we get these circular trajectories here. That was the rotational aspect of complex number multiplication. Now have a look at the dilational, or the scaling effect of complex number multiplication. Now what I'm going to do here is multiply each one of these complex numbers, each one of these dots, by the number 1.025. So that's all real part and no imaginary part. And have a look at what happens. Each one of these points gets moved just slightly further away from the origin. And now we combine both the aspects of complex number multiplication, the rotational aspect and the dilational or scaling aspect. So now what I'm going to do is multiply by the complex number 1.025 times the cosine of 3 degrees plus 1.025 times the sine of 3 degrees. And now we observe what happens when we successfully multiply by that. And hopefully you can quite clearly see that we get spiral shaped trajectories here. And with that, I'll conclude this video, and hopefully you've enjoyed this brief discussion on complex number multiplication. If you enjoyed the video, please like it, share it, and if you enjoy my videos, subscribe to my channel, leave some comments, and thanks for watching.